So, how much do we know about the future climate? So, I've been working on climate tipping cascades, these have a big impact on how much we know about the future climate and what we think might be happening, and then in turn on impacts on cascading risks into human, social, and other areas. So, an initial question is, what is a tipping point? So, a tipping point is where the system qualitatively changes its response to our forcing. So, for example, here we can imagine we're pushing this ball slowly up the slope, and then at some point, as we push it up, the more we push it, the further it goes up the slope. And this is quite a linear response to our forcing. But once we reach the top of the slope, if we push it a little bit more, it will continue going further. Let's not have that. Oh well. Keep clicking deny. You're welcome. So at some point, the ball will start to roll away from us. And this is a qualitative change in the way the system behaves. If we push it more, it will keep rolling away from us. The only way we can avoid it is by pulling back a lot. So these tipping points can have a big impact on where we end up. There are also things called tipping point cascades, which are important. They're in the title of the talk. And you can imagine these a bit like dominoes. So we can have one thing tipping over, like a domino falling, but then it can hit other ones. And you might see a domino and think there's nothing that's going to cause it to fall over, but then if another one hits it, it might make it much more likely. And this is the same thing with climate tipping cascades. There are some elements we think are quite difficult to tip, but if they get influenced by other elements, they might become much more likely. The natural following question is this actually a real thing? Do these things happen in the real world? And what this plot is, there's a lot of detail on here that you don't need to look at, but basically this is a plot of temperature over the past 60 million years. And the two key things to take away from this are, firstly, it's been pretty flat and chill for the last 10,000 years or so. And in the past, there have been quite sharp jumps every now and then. And there are a variety of reasons for these, and there are actually a lot of these sharp jumps that aren't in this plot as well. And we think that tipping points and tipping cascades are likely to be responsible for a lot of these things. So rapid changes of 5 degrees being relatively common in these tipping cascades. And we think they could happen in the future. So again, these big shifts in climate, while they may not be existential on their own, could then cascade into other areas, leading to big impacts and big risks for everyone else. So that's why we're interested in them, and this is kind of our motivation for they seem to exist. We think they're real. However, this is our best way of studying them at the moment. This is a global climate model, and it's done by coupling an ocean model with these nice grids to an atmosphere on big grids. And we can couple in other items as well. So we could couple in, for example, ice, on the poles, or ice sheets, sea ice, as well as the biosphere, things like plants, trees, plankton. And different models do these in different ways, but these are kind of the gold standard for studying these tipping points and for studying the climate in general. But despite these kind of centuries of scientific research, we don't have a great deal we haven't observed any of these tipping points. We actually struggle to model them, which we will talk about a bit more in the future. And so understanding how to go forward with these tipping points and how to predict them or understand how likely they are in the future is something that we need to work on quite a lot. So, as I said, we still have a lot of uncertainty in these tipping points. Our models struggle. And this is a figure from a recent paper, which is a summary of the uncertainty in these tipping points. So each of these red bars represents a different tipping point. It's not super important to know which ones they are. The important thing I want to draw your attention to is the range in these uncertainties. So this is temperature on the y-axis. And these ranges can be 4, 5, 6 degrees. So some of these tipping points we have a huge uncertainty about when they might tip, what the threshold might be, and some of them we even have uncertainty of whether they exist, whether they're a tipping point at all. So there are really high uncertainties here. The other thing I'd like to draw your attention to is this line here, which is our current warming about 1.2, and this kind of range between 1 and 5-ish, which is what we expect we might get to over the next century or two. And hopefully you can see that a lot of these tipping points at least have a possibility of having a threshold in that region, and some of them, almost the entire probability is within that region. So it seems likely that these are a risk we should be taking seriously. And obviously, it would be great to reduce all of these uncertainties. It would be great if we just knew more about all of them. But we have limited resources, and so the aim of my research is to try and help reduce these uncertainties and work out which of these uncertainties are most important to reduce. So it's likely that some are going to have a bigger impact on where we end up, some are going to be more important for these tipping cascades. So the model that I've been using is a very simple model. It represents 6 of these tipping points. Again, the names are not super important, but basically we represent each of these tipping points, these circles here, as a simple differential equation with a threshold temperature, so a temperature over which it will tip independently of anything else, and a mean tipping time. So when you tip it, that's the rough time it takes. If you raise the temperature by much more than its threshold, it will tip faster, and you can make it tip slower as well. And then we've also introduced these linear interactions between tipping points. So tipping points can interact with each other, perhaps making it easier to tip something, so lowering the temperature required. So a red link on this diagram represents a destabilizing effect. So if the Greenland ice sheet up here tips, it makes it easier for the Atlantic meridional overturning circulation here to tip. And in the other way, there's a blue link. So if the overturning circulation tips, it makes the Greenland ice sheet less likely to tip. So we do have this range of links. And if you spend some time looking at this, you'll notice that some things are more central and more linked than others, and some things have more red links, some things have more blue links. So it seems likely that different links are going to have differential importance. So what I've done here is look at the contribution to the overall variance. If we look at the number of variables that tip at the end of a run, which of our variables are responsible for that variation? So this is the fraction of variance explained by the uncertainty in each variable. These down here with the kind of TC are the temperature thresholds. So this is the temperature threshold for the Greenland ice shelf, likewise for the West Antarctic. And hopefully you can see that actually some of and these are the top 5 for runs at 1.5 degrees and 4 degrees, and hopefully you can see that some things dominate these much more than others, and there's also a tail of like 20 more that I haven't included on here. So this can really help us to focus our energies on the most important things, and we can reason about this a bit as well. So at low temperatures, the thresholds seem to be the most important thing, because actually at low temperatures it's just really hard to tip these things, and if your thresholds aren't roughly in that area, you just can't do anything. So for low temperatures, the thresholds are most important. Whereas at these higher 4 degrees thresholds, many more things tend to tip, and so the most important things are things with high thresholds like the El Nino, or things like the Greenland ice shelf, which have these stabilizing, that blue link I showed you earlier, which might prevent it from tipping. So we can kind of reason about which of these might be most important. But what if we miss something out? What if we've neglected something? What if we can't model something? What if it's too expensive? What if we just don't know it exists? So for example, what if we miss this stabilizing link here, this blue one from the AMOC to the Greenland ice shelf? Now, if we remove that, suddenly the Greenland ice shelf is much easier to tip and is much less stabilized. And it can go from at 1.5 degrees, about a 10% chance of tipping, to about a 50% chance of tipping, which is a huge kind of qualitative difference, and likewise, about double the chance at 4 degrees. So if we miss even one element of this model, because of the complex, chaotic nature of these models, they're very responsive to removing single elements. And so it means that if we're missing even single elements, our models can be badly wrong. And likewise, if we remove a whole node, so if we remove the entire Greenland ice shelf, this is again very similar to our previous ones. So this is representing a 10% chance that the Greenland ice sheet tips in the control run, but then we've just stacked on top the other elements, so the orange is the chance the AMOC tips, and then there are other ones that are less important. And this is our control run, this is what we think will happen if the Greenland ice sheet is included. And there are a few ways we can consider this. This second one is what happens is exactly the same. We've run the exact same dynamics, but then I've just taken this blue bar off the bottom. So this is what you might imagine if a model's perfectly doing the dynamics, getting everything right, but we're just not counting what the Greenland ice sheet's doing. And this is what we might like a client model to do in our ideal thing. Get everything important right, but just not count the thing. And that's what we might hope they're doing. But then this is what they're actually doing. This is where they're missing the green ice sheet, and they're a factor of 2 wrong in the total amount of stuff. So not only are they missing the contribution from the green ice sheet, they're missing its cascading impacts down. And you can be a factor of 2 out and be very wrong, even if you're missing single elements. And so the huge impact of missing these single elements, you might think, oh, that's great, but surely we're not missing things. So this is a summary of some of the things that we're missing in some of the climate models. So I've kind of put an X on things that are missing in some climate models. So lots of climate models don't have the ice sheets in them. They're just not there. So any links to and from the ice sheets are not present. Some models do have ice sheets, but they only couple one way. So the ocean can impact the ice sheet, but not vice versa. So we lose these links. Some don't have biosphere. And some have a AMOC that's artificially, in some way, very, very stable, and so can't tip. And so we kind of lose this very central link that we've spoken about. So there are reasons to believe that our climate models are missing some of these details and might have issues in predicting these tipping events and might be much more stable than we would expect. And this, I think, is a strong motivation for this kind of epistemic honesty. So the climate is very complex, and if we miss a single element, we can drastically damage our predictions of it. As I've just said, it's very likely that our current models are missing key elements of dynamics, and so we should treat their predictions with significant doubt and uncertainty. So even if they are our best models and our best estimates, we should be honest that we may be missing things, and actually the worst case may be worse than that, the best case may be better. We should put a much greater cone of uncertainty around these climate models. So to conclude, we can better focus our energy for future climate tipping points research, focusing on the most important variables, the ones that are most likely to tip at low temperatures, the ones that are most likely to initiate these cascades can make a big difference. If we miss out key elements, we may lead to a significant kind of factor of 2 error in our projections. And due to the uncertainty in the behavior of the climate system, we should act under greater uncertainty if we're less confident in the predictions of our models. So we could perhaps adopt a precautionary approach where we assume that we're missing something and perhaps be more aggressive in our emissions reductions to avoid risking climate tipping points that we're not aware of. And I'll just finish off with a big thank you to my supervisor, Nico Wunderling, research manager, Gideon Futerman, and all of you for making the ERA Fellowship so much fun. Thanks.